Let's look at an example where we are asked to use the divergence theorem to calculate the surface integral of f.ds, that is the flux of f across the surface S, where f is this field given, and S is the surface of the solid bounded by the cylinder x squared plus y squared equals 1, and the planes z equals x plus 2 and z equals 0. So let's get a rough sense of what this thing is going to look like. Oh, actually, I need to back that up this way because this is a cylinder. We have a cylinder centered on the z-axis, so we need enough space around here to sketch that. The lower bound is z equals 0, so that's fine. We can kind of sketch some cylindrical thing that will be coming out here. Let's see here. This is a little bit tricky to draw. This is probably not going to go very well at all. We have this slanted plane is the problem here. And trying to draw this in perspective is a little bit challenging, to say the least. The lower bound is easy, z equals 0, that's the xy plane. The upper bound is this plane z equals x plus 2. So it has this sort of slant to it. If we look at this straight on from the perspective of, so if we have z and x, so y is coming straight towards us. So this is the positive y direction. So we're on the positive y-axis looking at this. Then we have something that is kind of slanted like this. This is the kind of cylinder that we're looking at. The base is horizontal, but the top portion is cut off at an angle here. So we need to calculate the flux of F across S. So we see that this S being the boundary of this solid, right? It's the surface of this solid. So it has three distinct pieces. There's the base here, there's the slanted plane there, and then there's the side, which is part of a cylinder, which can be described parametrically, but if you didn't, if we don't do this parametrically, we could split the cylinder and turn it into a couple of functions. So we could break this up into 4 pieces maybe, but those surface integrals are starting to sound very unpleasant, right? The key here, of course, is that the divergence theorem is very nice because when we are trying to compute a flux across a closed surface like this, it encloses an interior, and the flux across a surface has to equal the divergence of the field throughout the interior of the surface, right? If the field is incompressible, the net flow in equals the net flow out, so the flux would have to total to be 0. If you have positive flux, that means that more is coming out than is going in, so there must be a net spread inside, the divergence must be positive, and so on. So let's use our divergence theorem, as we were told to do, and first compute the divergence of our field. We know we're going to need that because it's sort of right there on the tin. So that will be the partial of, actually let me write it this way. That's a little bit easier, I think. We have del dot f is a good way to remember this, I think. So we have the partial by x of the first component. So we get, looks like 4x cubed, plus the partial by y of the second component, that is 0, plus the partial by z of the third component, that is 4xy squared. So we have this thing, which I'm going to, so we could simplify this as 4x cubed plus 4xy squared, obviously. But looking at setting this up, we see we have this cylinder here. We're probably going to be moving towards cylindrical coordinates. So let's go ahead and factor out what's in common. There's a 4 and an x. And when we factor that out, we are left with an x squared plus y squared. And that is perfect. Right? This is very promising. Because now we see that we can just set this thing up in cylindrical and say that, okay, well, we wanted the flux of F across S. The divergence theorem tells us that that is the triple integral over the region we often call E, but it's just the interior of S, of the divergence of F throughout that volume, dV. We've been doing a lot with these crazy like vector things, but the divergence, remember, is a scalar field. So this is just a triple integral of a chapter 15 style. We have the triple integral over E of that divergence, so we computed to be 4x times x squared plus y squared dV. Now, we know that the region here is this cylinder of radius 1, but the upper bound on z is x plus 2, so that suggests cylindrical coordinates, where z goes from 0 up to x plus 2. Now in cylindrical, x is r cosine theta. Okay. And we have this in here, so we have 4 times x, which again is r cosine theta, times x squared plus y squared is r squared, times dv. Now dv is going to be r times our differentials. We need z on the inside because of that r cosine theta business, so let's put the dz on the inside. And then outside of that, it doesn't really matter, I don't think. We can just do dr d theta. So r goes from 0 to 1, theta goes from 0 to 2 pi. Again, this 1, of course, is because of the radius of the cylinder. X squared plus y squared equals 1. So we have this business. We can't separate this, at least not just yet, because we have this r cosine theta. So we are going to have to, although what we can do, let's see, we have the integral from 0 to 2 pi, of the integral from 0 to 1. We can combine all of this stuff. We get, it looks like 4r to the 4th cosine theta times, so we're integrating, this is constant with respect to z, so I can kind of pull that out, integrating there, so we get z evaluated from z equals 0 up to z equals r cosine theta dr d theta. So we have the integral from 0 to 2 pi of the integral from 0 to 1 of 4r to the 4th cosine theta times, that's going to be r cosine theta minus 0. This is r cosine theta dr d theta. And this now is nice because we can finally separate this, right? We can write that we have the integral from 0 to 1 of 4r to the 5th. I suppose I could have pulled the 4 out front. I'll probably do that in the next step. Dr. Times the integral from 0 to 2 pi of cosine squared theta d theta. So let's see what this works out to. We'll have 4 times, that is going to be a 1/6 r to the 6th from 0 to 1, times this integral here, that is the integral from 0 to 2 pi. We need a power reduction on the cosine, right? That is 1 plus cosine 2 theta over 2 d theta. So it looks like we have 4/6 or 2/3 times this integral. So we're going to have 1/2 of integrating this. Integrating 1, we get theta. Integrating the cosine 2 theta looks like a 1/2 sine 2 theta. We will find out in a moment if I'm doing this at all correctly. So combining that, we get 1/3 of 2 pi plus 0 minus 0. So this looks like 2 pi over 3. And let me check my notes. Yes, that is in fact the solution here. We get 2 pi over 3. Okay. The divergence theorem is a wonderful theorem. It's difficult to use in the other direction. It applies in principle, but in practice, I'm not sure how often you want to evaluate a divergence and you end up reconstructing what field, rather, I'm not sure how often you'd be evaluating a triple integral and then trying to reconstruct what field would give you that. Although if you know it's a divergence of a particular field, then you could try this out and see how that goes. But most of the time, this simplifies in the other direction. Surface integrals can be kind of a pain sometimes, but as long as they enclose a boundary that is easy to describe, we can try computing the divergence, which often simplifies things considerably, because you're taking a vector field and reducing it down to a scalar field. And if things are nice enough, that usually helps. Some functions get worse when you differentiate them, but especially when you have polynomials like this, those tend to get cleaner. So that is quite nice. And this divergence theorem allowed us to reframe this flux question into a question of finding the total net divergence throughout that region. And a little bit of work to grind through, but not nearly as bad as it would have been evaluating that surface integral directly, simplifying down to that 2 pi over 3.